let us start this lecture 32 and let us recall what we learned in the last few lectures. We basically looked at the ideal cycle analysis covering various engines, namely ramjet engine and turbojet engine, turbofan engine and turbojet with afterburner and the turboprop engines, and we have taken several examples to illustrate how we can estimate the various performance parameters, and also we had carried out the parametric analysis to understand which factors plays important role in the performance parameter. Keep in mind that all these things are based on the what you call without any geometry. You are just playing around as a designer to look at what really you want to have particular mission requirement. Now, we will be discussing about how to carry out a real cycle, because all those things we did under several assumptions. Now, we will remove those assumptions and see how we can really carry out analysis which will be more realistic. Still we are doing some kind of, or we will be doing some kind of approximation as well, but that is good enough, that is rather better than the ideal one. So, what we will be doing if, in this case we will be looking at the losses incurred in the ideal in the what you call real gas turbine engine, and we have not considered any losses in the ideal cycle analysis. However, we need to look at. So, if you look at losses, all the losses kinds of, there are various kinds of losses, we can divide them into how many categories. What are those losses? For example, flow is occurring in a air intake, right. It is occurring through the compressor or the turbo machinery, turbine. That means there will be some losses due to frictional losses, there might be separation, there might be mixing. So, those are losses. Beside this, there will be some transmission, right, and the transmission of power from turbine to compressor, turbine to propeller, right, and there will be all the power given by the turbine cannot be transferred to the compressor, right, and there will be another kind of losses which will be basically due to the heat transfer, and we because when the flow is taking place it is combustor. So, it can be. So, broadly it can be divided into three categories. One is aerodynamic losses, other is thermodynamic losses, and the third one is the mechanical losses, right. And aerodynamic losses, as I told, it is basically due to the fluid flow through various components of engine, which is quite complex in nature, particularly in turbo machine, and it will be adverse pressure gradient like in compressor, air intake and other places. If you look at your combustion chamber, it is quite complex, particularly the main combustors, even the afterburner, there will be blob bodies, there will be mixing, there will be losses. So, those are aerodynamic losses, and thermodynamic losses is due to incomplete combustion of fuels, right. Not that all the fuel you can't really convert into the energy, it is not possible in real situation, because it will be operating over a wider range during its operation. And beside this, heat transfer is inevitable, although we have assumed there is no heat transfer, right. It is inevitable to the from the component to its surrounding, and as I told you, the power transmission has to be taken place from turbine to the compressor to the propeller, and then there will be some losses. So, all these losses we need to now consider, and let us see how we will be working with it. And let us ask question, how does the real cycle performance differ from that of an ideal cycle? What are those things? If you look at, we have assumed in the your all the components having the all same properties like air, we say air standard ideal cycle, right. But in real situation it is not the air alone, from the combustor onwards it will be the several other combustion products, fuels and other things will be coming, number one. Number two, temperature is changing from intake to the nozzle exit, and of course peak temperature will be occurring in the combustion chamber, right. So, therefore, the Cp values will be changing, gamma will be changing, several kinds of things will be occurring, which we have not considered, right, in our ideal cycle. So, as I told you, variation in gas properties throughout the engine owing to both temperature, pressure and composition. It is not the composition which is changing, but also the pressure and temperature is changing. So, and non isentropic diffusion process in air intake and compressor. Similarly, non isentropic expansion in the turbine and nozzle, right, but in real like ideal situation we have all considered isentropic processes, right, both for the compression and expansion. So, change in kinetic energy and potential energy between inlet and outlet can be ignored all the components of gas turbine engine. Of course, that we will be considering, because we are interested to look at the total one, and of course, potential energy is now very important, particularly for case of a gas turbine engine, because all will be in the similar level. But when you use the centrifugal compression and centrifugal turbine, we need to worry about, but those contribution will be very less, right. But in case of steam turbine and other thing, you might be knowing its potential energy plays small role, but here in this case we need not worry about it. So, there is another one which of course I will not be discussing, but you can note that bleed air extraction from the air intake and compressor for turbine cooling, because we need to cool the turbine, right, and it is basically this air which will be causing problem in case of your air intake and compressor, right. You will just transfer this problem due to what? Problem due to surging, flow separations and other things, due to adverse pressure gradient in case of air intake and compression. Those which are the problem now you will be using for cooling the turbine. It is a win-win situation kind of thing, right. That is the kind engineers they have developed, how to overcome the problem, at the same time solve another problem. So, incomplete combustion of fuel, gas dynamic losses in the combustor due to heat addition, the flow in the exhaust nozzle may not be fully expanded to the ambient pressure, rather it will be over expanded, under expanded, depending upon its operating envelope. If you look at gas dynamics, we have already seen that Rayleigh flow, that is basically we have already talked about it, how it will take care of whenever heat addition will be there, there will be losses in the pressure, total pressure. So, let us look at how this Cp will be varying with the temperature, because across the engine it changes from temperature 300 Kelvin to it can go to even 2000 Kelvin, particularly if afterburner is there, right. So, if you look at the Cp values, it will be dependent on phi. What is this phi? Phi is basically equivalence ratio, right, which we have already defined, right. So, if it is 1, right, you will get a higher Cp values, and keep in mind that the Cp I have shown, these are the Cp values. Cp is increasing with respect to temperature, that means it is increasing, and as you are having what you call 1, and this is phi is equal to 1, and as it decreases it become a 0, this phi is equal to 0, the smaller one. But whereas the specific ratio gamma, that is Cp by Cv, right, it is decreasing with respect to the temperature for all equivalence ratio, and keep in mind that this is basically phi is equal to 0 and this is phi is equal to 1, and it is just opposite of that of the Cp, right. So, that means we need to take care of while analyzing the real cycles, because each components there will be change in temperature. But however, for computer program one can do this thing, but for hand calculation we will be not using this, because it will be very cumbersome. Why? For air intake there is a change in temperature, now I will have to calculate along the air intake how it is, right. Similarly, in the compressor or combustion chamber it will be very difficult job, do a hand calculation, but in computer program I can have, because Cp is a function of temperature, we can get coefficients and it is also a function of species, right. It is dependent on species. For methane, for oxygen, for some other, then you will have to calculate average Cp. So, it is a quite cumbersome. Therefore, we will be using till compressor 1 gamma, right, that is gamma 1.4, and for the combustor onwards we will be using another gamma, right, gamma g, right. And similarly, Cp will be using 1.005 kilojoule per kg till compression, exit of compression, and inlet of combustor onwards we will be using another Cp. That means, 2 Cp will be using Cpa, Cpg. That is for the simplicity. Again, we are doing an approximation here, just to make it problem tractable, which can be solved by hand, right. So, let us look at air intake pressure recovery, and if you look at, this is an air intake, and these are the lifts, right, in which the air will be entering into the air intake. If you look at, there is a divergence of the streamline. What it indicates? What it indicates? There is a divergence here, it is diverging. What is the indicates? Two-way continuity, movement, balance, mass balance. If you do, what will happen? Area is increasing. If area increasing, what will happen? If keeping the density is remaining same, so velocity will be decreasing. That means, this is deceleration, right, or diffusion you can call, and this is what you call external diffusion, external compression you can say, because there will be increase in static pressure, right. And of course, however it is going through the, when it is entering, this is known as internal compression, because if you look at air intake is a air getting compressed, because decelerated, right, the flow is being decelerated. And there might be a situation where it will be other way around, it will be accelerated in the your external portion 0 to 1, right. Will it really occur? When?
When the velocity is very less.
For example, under what condition?
When the aircraft is
standing, or it is about to take off, or it is climbing, at that kind, this will be is a different, this streamlines if you draw, it will be wrong. So, I am not going to discuss, but you please think about that, right. So, now if I look at the processes in Ts, what is happening? This P naught is the pressure, static pressure, free stream static pressure, and there is a compression, and this is compression 0 to 1, right, will be what? Isentropic compression. Am I right? Can I say isentropic? Can I say or not? Because there is no surface, right, and also this compression is the heat losses will be very, very low. So, adiabatic and reversible, because there is no losses in friction and solid surface is not there. So, therefore, it will be like this isentropic compression, but whereas these process, if you look at P1 to Pt naught, or right, if you look at Pt naught or Tt naught, this point is equal to the Tt2. So, this process is basically the isentropic compression, right. But however, as the solid surface is there, so it will be having a lower pressure over here Pt2, that means Pt2 is less than Pt naught, right. Agreeable, disagreeable?
If so, it is not isentropic, no sir.
It is not isentropic, this is not an isentropic process, whereas the T2s I am saying this is isentropic, S for isentropic I am using, whereas it is not isentropic. That means, this dashed line is not an isentropic. So, and the pressure P2 is the static pressure, that means there will be change compression, and I have indicated in the dashed line. Okay. Keep in mind this velocity V2 square by 2 Cp, this portion V square by 2 Cp, this portion, right. So, what we will have to do now, how to handle that, that is because as I told, it is basically air intake to decelerate the free stream fluid smoothly to a lower velocity, either in subsonic or supersonic, and this is basically a subsonic diffuser, air intake, right. Right. But the supersonic is there, then shock will be there, you need to take care of that, which I am not discussing, but it can be handled in the similar manner. I will be talking little later on. So, the what are the causes of losses? Frictional losses and shock losses in supersonic diffuser, right. Diffuser or air intake, both are interchangeably can be used. So, the pressure recovery factor is basically, we need to define a pressure recovery factor, that is basically ratio of average stagnation pressure at the intake exit to the free stream value. Why average? Because in each point it may be changing. So, therefore, I need to take average in real situation, right. Here we are considering it to be flow to be one dimensional, in real situation flow can never be one dimensional. So, I will have to take average values. So, therefore, it will be PT2 divided by PT naught is nothing but pressure recovery factor pi d. Always it will be less than 1, right. This will be less than 1.
So PT2 divided by
PT2 divided by PT naught. PT naught is here. If I convert all the total and that velocity V naught, P1 P naught plus V naught square, this is this portion, right. Total will be PT naught. So, PT naught is much higher, or rather not much higher, it is higher than the PT 2. So, therefore, it is less than 1. In ideal cycle we have assumed it to be 1, pi d is equal to 1, but it is not 1. Is that clear in real situation? So, assuming the processes in the air intake to be adiabatic, but however, we are considering the process to be adiabatic in the air intake. Why? Because the change in temperature between the ambient and this thing will be very low. So, therefore, we are assuming again in assumption, because it can never be in principle. So, the PT, as I told you, PT2 by PT naught actual will be less than PT2 by PT naught, and PT2 by PT naught is basically 1 in case of ideal, right, it will be less than 1. Hence, the isentropic efficiency is given by, we can define eta id is equal to S2 T 2 S minus H naught, that is the free stream, divided by S T naught minus H naught, and we can assume again Cp is same during this process, right. Therefore, it is approximate, but is not the really true, because Cp will be changing, right. As in our real analysis we have assumed that Cp will be remaining constant till the compressor exit, then we can manage this with this. Is that clear? So, if you look at this is basically what I am saying, this is Tt 2 S minus T naught and Tt 2 Tt 2 Tt 2 S minus T naught divided by Tt naught minus T naught, like that is the isentropic efficiency for a air intake, for an air intake. So, if I look at this is basically Tt, I can write down, I can divide this by T naught and I will get Tt 2 S divided by Tt naught minus, no, that is a little problem here, okay, right, this is not. So, this I can write down, this is basically not Tt 2 S divided by Tt naught into Tt naught by T naught, right, and we know that Tt naught by divided by T naught is nothing but 1 plus gamma A minus 1 divided by 2 m naught square, is not it, right. If it is isentropic flow, because this portion is isentropic, right. So, therefore, I can write down, and this is nothing but Tt 2 S divided by T naught, this is nothing but a pi d gamma minus 1 divided by gamma. Keep in mind that here it is gamma A, this is gamma A. So, and in of course, if I put this is basically this is nothing but your tau r, this portion. So, if I what I am doing, it is basically eta d is a function of flight Mach number, and also it can be related to the pi d. If I know this pi d at values, because pi d when Mach number is very low, it is towards going to the 1, yes or no, pi d will be 1, because there is no flow, I am like it will be 1 kind of, it is going towards 1 and it will be decreasing with the Mach number, and if I know these values I can get what will be the eta d, which is lower than this values, right. So, you can get a relationship between the isentropic efficiency for an air intake with respect to the what you call the pressure ratio across the air intake or the diffuser. So, the overall pressure ratio intake can be expressed as pi d, because we need to know this pi d will be pi d maximum into pi r, and this is pressure is due to ramming effect, because particularly in supersonic flow the ramming effect will be very very high, and this pi r in the subsonic flow or the low subsonic flow will be almost equal to 1. We will see that. So, the pi d maximum is certain portion of ram total pressure due to wall friction, because wall friction will be there. So, therefore, this value will be having certain thing, right, which is due to wall friction, whereas pi a certain portion of total pressure due to ram recovery, right. And now, to get this pi r is not that easy. What we will be using an empirical relationship, which of course was being derived long time back in maybe in 60s, okay, that till we are using pi r is equal to 1 and m net less than equal to 1, very very low subsonic or the subsonic flow, right, it will 1, whereas the m naught 1 to 5 you will have to use this expression, and when the m naught is beyond 5 you will have to use these expressions, right, particularly supersonic very very high rather hypersonic flow you will have to use, and this case is supersonic flow. This is basically supersonic flow. So, item is very handy in for handy to use in the cycle analysis, but however, it is not easy to measure the total temperature, right, not the static temperature that easily. However, one can measure the total pressure very easily, right. So, therefore, in experiment people use the total pressure, and in cycle analysis we always use the isentropic efficiency, right. So, that you should give, but of course, there is a way of doing it, and ram efficiency is defined as basically, that is why ram efficiency eta r d is P T 2 minus P naught divided by P T naught minus P naught. Keep in mind that this is not pi, this is eta, okay. Of course, one can convert into the P T, and this eta r d is found to be almost same as I d, but is not same, I mean it is approximately same. So, it is easier to evaluate the experimentally, but it offers no specific advantage over I d, right, particularly for cycle analysis. So, and location of the engine in aircraft, for example, in the wing, pod or fuselage dictate the air intake efficiency, right. For example, in fighter aircraft your air intake will be in the fuselage itself, and there will be maybe serpentine duct sometimes being used. So, therefore, efficiency will be different than the your Boeing kind of series, right, or the larger aircraft. So, now we will be looking at how to handle these losses in compressor and turbine efficiencies. In actual compression and expansion process, losses basically are caused due to viscous shear on the blades and the walls of the casings, and also the mixing, two blades will be there, will be mixing at the downstream in the wake regions, all those things, because of that the losses will be occurring, right. And how to take care of that is basically we need to look at a processes in TS diagram. If you look at this is your station T2 and the pressure corresponding PT2 and temperature TT2, and if you look at this is the ideal or isentropic process from TT2 to T3 TT3S, S for isentropic, and whereas the real one which is shown in a dashed line will be from pressure PT2 to PT3, and of course, temperature TT2 to TT3. What it indicates? That means for the same pressure ratio, right, in a compressor or getting compressed or getting, then you need to provide more amount of work in case of real situation than that of the ideal one, right. That is the meaning, because a lot of things will be lost and which you need to provide to get the same pressure ratio. That is very important point you should keep in mind. And similarly, we will let us look at for the expansion process in a turbine, that is station from TT4 to TT5. If you look at, this is the isentropic process, the vertical straight line, and the dashed line is for your real one, right. What it indicates? What is it indicating? It indicates that the more amount of work will be produced for an ideal case for the same expansion ratio. In other words, less amount of work will be produced in real situation as compared to the ideal one for the same pressure ratio of expansion, right. Compressor, it is other way around, right. That means you need to give more amount of work in real situation to produce the same pressure ratio. So, we will be now looking at how to handle that, and we can define very easily with the using the similar what we did for an air intake. The isentropic efficiency of a compressor can be given as ideal compression work output for a given pi c divided by actual compression work input for a given pi c. So, and what is that meaning? Meaning is that, like, what is the ideal work is basically H T, the amount of work for ideal will be H T 3 S minus S 2 S T T 2, this portion, right, divided by the amount of work from here to here, that is S T T minus S 2. And if I assume that C P is not changing, so it is approximately is that. So, and then I will divide this, I can write down here the T T 3 S minus T T 2 divided by, if I divided by this T 1 T T 2 and here also T T 2. So, this is T T 2, I will get T 3 S divided by T T 2 minus 1 and T T 3 divided by T T 2 minus 1. If you look at, this is nothing but your tau c, and this is for isentropic process, because we are talking about here in the isentropic process, right. So, therefore, it will be pi c power to the gamma a minus 1 divided by gamma a, and this is in pressure ratio across the compression, right. So, isentropic efficiency of a turbine you can write down in a similar manner, that is T T 4 minus T T 5 divided by T T 4 minus T T 5 S, and you can write 1 minus tau t divided by 1 minus pi t power to the gamma g minus 1 divided by gamma g, right. You can look at your diagram and then do that, but the same thing it will be, right. So, question arises, we need to whether use this isentropic efficiency or we will go for something, because isentropic efficiency will be changing in a compressor, because if you look at in modern days the compressor or pressure ratio of even 40 people are contemplating to use. That means, there are several number of stages, right, and then whether this isentropic efficiency we can assume to be constant for such a high pressure ratio or not. And you will be surprised to know that it is not that prudent to use the constant isentropic efficiency across the all stages of a modern compression, right, axial compression particularly more number of stages. So, therefore, we need to define a polytropic efficiency. Polytropic efficiency is basically what you call a ratio of ideal to actual work for an infinitesimal step during a compression process. That means, if I am going, let us say from pressure P T 2 to pressure P T 3, right, and then there will be number of stages which will be there, right. And what I am saying, this is a in a very infinitesimal, let us say this is P T and this is P t plus d P t when d P t is tending towards 0 or very very small, right, infinitesimally small d P t. Then we need to look at, and then we will define this isentropic efficiency and connect to what you call this polytropic efficiency to isentropic efficiency across the entire compression consisting of number of stages. So, let us do that. That is polytropic efficiency basically ideal compression work input for an infinitesimal pressure change, that is dPt. dPt is very very small, right, divided by actual compression work input for an infinitesimal dPt pressure, right, change. Keep in mind we are doing for compressor, and we will be looking at also for the turbine. So, considering incremental pressure rise P t plus d P t as shown in T s diagram, you can see that is basically if you look at this efficiency will be T t d t s divided by d t will be nothing but your polytropic efficiency, because this is for isentropic, this is for your isentropic, and this is for your what you call the actual, right. So, therefore, eta P c will be d T s divided by d t. I can write down d T s divided by d t, d T t divided by t t, right. I can write down this very easily, and for infinitesimal isentropic pressure change, the temperature and pressure ratio can be related. For example, I can write down this as d T s, I can write down d T s by d t is equal to d P t by P t gamma a minus 1 gamma, because this is isentropic. So, I can write down very easily, yes. So, I can write down 1 plus this, 1 plus this will be 1 plus that, right, and then I can write down this. And what I will do now with this, I will be using the binomial expansion, because this is very very small quantities, right. I can rewrite this as d t s by d t P t plus d P t what you call divided by P t power to the gamma minus 1 divided by gamma. And if you look at this expansion, I can I can expand in a binomial series, and neglecting the higher order terms, I will get 1 plus d P t divided by P t is nothing but 1 plus gamma minus 1 divided by gamma d P t P t, right. So, if I substitute these values here, what I will get, because in place of this I am substituting here, what I will get? I will get gamma a minus 1 gamma a d P t by P t, is not it, 1 cancel it out. So, that you will get. So, using this equation, because this is equation 4 and equation 1, this is basically equation 1 if you look at. So, what I will do, I will get d T s by divided by d t is nothing but gamma a minus 1 divided by gamma a d P t divided by P t and d t by d t. So, if I just work it out, I will get d t by t is equal to gamma a minus 1 divided by gamma 1 over eta P c. Eta P c is basically the polytropic efficiency d P t by d t. Now, if I integrate this expression, I can get is equal to basically d t 3 by d t 2, that is for the entire range, right, because I have taken a very small thing and then I am integrating over the station T t 2 T t 3, I will get P t 3 by P t 2 power to the gamma minus 1 divided by gamma a eta P c is equal to, if you look at, this is nothing but your pi c. So, I can write down pi c gamma minus 1 divided by gamma a eta P c, that means this power will be there to the pi c. By this using this one, I can really go back and relate this polytropic efficiency into isentropic efficiency. So, if you look at, I will put this isentropic efficiency by definition T T 3 S divided by T 2 minus 1, and this is nothing but pi c gamma minus 1 divided by gamma a, just for isentropic process, because this is an isentropic process, you know, you can isentropic, right. And whereas T T 3 by D T 2 is nothing but your, you know, similar to isentropic process, but there is a comes a polytropic efficiency, right, minus 1. So, now I can get this isentropic efficiency related to the polytropic efficiency, right, for a certain range of pressure ratio. We will be doing that in the following the similar ways, you know, we can also derive for the turbine, but keep in mind that difference between this eta IC isentropic efficiency and polytropic efficiency of compression increases with the number of stages, right, and also with increase in pi c pressure ratio across the compression. Because why it will so, and as the pressure ratio increases, there will be increase in temperature caused by the friction, and this increase in temperature will be cause more compression work in the subsequent stages, right, and this process is known as preheating effect. That is the reason why intercooling is being used to reduce the work input to the compression for the same pressure ratio. That is why I told you, like, we will be using some kind of a alcohol or a water injection, right, in to enhance the performance of the compression, right. So, because the preheating effect has to be nullified, we know very well, like if the temperature is higher, so to get the higher the same pressure ratio, you need to provide the more working. Derive an expression for eta IT in terms of eta PT and pressure ratio across the turbine, right. So, if I take this, two values I am taking, one is PC, that is the polytropic efficiency of compressor 0.85 and polytropic efficiency for turbine 0.9, and varying this pressure ratio, you can see that this isentropic efficiency goes on increasing in case of a turbine, and in the case of compressor it is just opposite, is decreasing because of preheating effect, right. There it will be cooling effect, just opposite will be happening, right. So, now we need to look at the combustor efficiency and pressure losses. Keep in mind that we will be using those whatever analysis we have carried out to take care of the losses in components, various components, air intake and compressor and turbine, we will be using real cycle analysis, and combustor efficiency and pressure losses. If you look at this efficiency of a what you call combustor will be affected, will be lower than 1, because it is not possible to convert all the chemical energy of the fuel due to the imperfection of the imperfect combustion of the fuel and air, and there might be carbon monoxide, unburnt hydrocarbon, soot particulates, other things. Beside this, there will be stagnation pressure losses across the entire combustors, right, because of heat additions, and also there will be mixing, the flow is quite complex. So, therefore, it will be losses. That means, we need to take care of that. So, that means, we will be taking care of combustion efficiency, what we will be defining, that is as a ratio of actual change in enthalpy due to combustion and total energy released due to the calorific value of the fuel. Ideal, you cannot get all the calorific value to be converted into the thermal energy. So, if I consider this combustion chamber between station 3 and 4, and certain amount of mass air is entering at temperature T 3 and leaving with temperature T T 4. So, I can get eta efficiency nothing but m dot A plus m dot F S T T 4 minus m dot A S T 3 divided by m dot F into delta S C. Delta S C is the heat of combustion or calorific value. Generally, for ATF we consider 43,000 kilojoule per kg. Keep in mind that this pi b, right, will be less than 1 always, right. And what is this pi b? Pi b is equal to basically PT4 divided by PT3, and in ideal cycle we have considered pi b as 1, but here it will be 0.9598, as close as possible people go on designing it to bring to the or take this pressure ratio to be closer to 1, right. Closer to 1 means they will be more happy. I mean, of course, they have not achieved till that, but it is quite good. I mean, the progress is quite good. So, losses in exhaust nozzle. So, nozzle efficiency ratio of actual to the isentropic drop, that is we will be looking at nozzle efficiency, and again we are assuming mean Cp value for actual expansion process in nozzle, right. Then the if you look at the processes in the TS diagram, this is basically from station 5 to the 9, right. There are several other things are there, because if you look at TT5 is the exit of your turbine. If air intake will be there, then it will be TT7, right. Sorry, if the afterburner is there, there will be 5 to 7 is the this thing, 7, 8, 9, right. So, it is we can say either it is T7 or T5, right, both are same, but I am considering PT5. Then actual expansion will be from PT5 to P9, whereas the isentropic expansion will be PT5 to P9s, right. The T9s, but the pressure remains same, P9 is equal to P0, that we are considering. But when I will talk about the what you call turbojet engines, then we will be talking about choking condition, whether it is choked or not, right. I am not, let us define this nozzle efficiency, that is, and keep in mind that this is the same, this is TT5 is equal to TT9, because adiabatic we are considering. So, therefore, TT9 minus T9 divided by TT5 minus TTS, and if I divide this by the TT9 and divide by the TT5, which is basically same, right. So, you can get this thing, and this is a ratio, and we will be getting all those values, and we can express this TT9 as by TT5 in terms of pressure ratio P9 by PT5 power to the gamma g minus 1 divided by gamma g. The component efficiencies and losses of a gas turbine are dependent on the engine installation aspects and applications of the aircraft, because the different installation of the engine will be having different efficiencies, right. For example, in fighter aircraft you install the engine in the adjacent to the fuselage, is a part of fuselage, whereas in other places it is like a pod, it will be hanging from the your wing. So, naturally it will be, in some cases you may put on the back side of the fuselage. So, therefore, what you call it will be having different efficiencies and factors one has to. For example, for a long range subsonic aircraft with Nozzle mounted engines and fixed area of conversion nozzle, value of pi d and pi n will be much higher than that of supersonic fighter aircraft with a variable area conversion diversion nozzle. So, always for the fighter aircraft we use a variable area conversion nozzle generally, but nowadays people are coming up with the variable area conversion diversion nozzle, right. So, with this I will stop over. We will in the next class discuss about the real turbojet engines, carry out a real cycle analysis of turbojet engines. Okay.